Hi, and welcome to part 3 of our lesson 4 video, blueprint reading. Now, today we're going to be looking at dimensioning, and we're going to be looking at drawing layout, and ultimately how to go about reading a blueprint. But before we get to all that, I would like to take a look at tolerances. Tolerances are crucial. And there are many kinds. It all depends how you want to look at it. Now, there are really two big families of tolerances. There's dimensional tolerances and there's geometric tolerances. Now, obviously, dimensional tolerances will have to do with dimensions, and that's something that we're used to, or a little more used to anyways, because it's more common and we see it quite often. And that is something like 1 inch plus or minus 10/1000ths of an inch. Geometric tolerancing, however, does not apply to dimensions. Geometric tolerances apply to shapes. How square does a part have to be? How parallel do two surfaces have to be? How cylindrical does a part have to be? This is what geometric tolerances define. And we'll be looking at geometric tolerances after we complete our little presentation on dimensional tolerances. Now, dimensional tolerances are one of the two families, but dimensional tolerances can be subdivided into at least 4 separate groups. Now, we can have unilateral dimensional tolerancing, bilateral dimensional tolerancing, we can have specific dimensional tolerancing, and general dimension tolerancing. Bilateral dimensional tolerances, well, are just that. They have two sides. They are bilateral. And for that, well, we could say something like 1 inch plus or minus 10/1000ths. That's bilateral because we have plus 10 and we have minus 10 from our base dimension that was 1 inch. Unilateral tolerancing, however, is again just that. It's unilateral, one side only. Now, we can have as an example 1 inch plus 0 plus 10. So base dimension or a little bigger, but not smaller, unilateral. Now, I can hear the questions buzzing. Why do we want bilateral and unilateral? Well, really, bilateral is easier to use. It's what comes naturally. Tolerances have a plus or minus to them. We think that we can have a possibility of error in both directions, bigger and smaller, and that is bilateral. But if we're trying to get a proper fit, let's say between a shaft and a bore, well, unilateral tolerancing is a really practical way to go. Just so that it's clear, let's look at a little example. Let's say I have a shaft that's 1 inch plus or minus 10/1000ths of an inch, and I have a bore that's 1 inch plus or minus 10/1000ths of an inch. I could go with that assembly from a lot of interference to very loose. But let's say that I wanted to make an assembly that had a little bit of play, but never a lot of play. Well, it would be a lot easier to use unilateral tolerances. So let's look. 1 inch plus 1 plus 5. Okay, for my shaft. And let's take a look at my hole and say that I have a 1 inch hole, a minus 0, minus 5. Well, I'm sure that if I manufacture my part to those specifications, I will always have a little bit of clearance or a little more clearance, but I will never have an interference. And that's the gift that unilateral tolerancing gives us. Now remember, we have a little quickie video on fits, so if you want to refresh your memory about those, take a look at this. Here's the link for that. The other thing that I mentioned was that our dimensional tolerances could be general or specific. That's a little simpler to understand, because a general tolerance is one that applies to the whole drawing, and those are the tolerances that are generally specified in the drawing header as a XX or a XXX or a XXXX indication of plus or minus 1, 5, 10, or whatever. And each x, well, is relative to the number of decimal points that show on the dimension on the print. That is a general tolerance because it applies to the whole drawing. Now, some dimensions on the print might not need that general tolerance. They might need a more specific tolerance, and at that time we affix on the drawing itself and not in the header a specific tolerance for the dimension. And that's when we'll see a dimension on a print with a plus or minus directly next to it. That's a specific tolerance. So let's take a few minutes and take a look at some example drawings where we can see different ways of tolerancing dimensions. Remember that I've mentioned on several occasions that to be manufacturable, a part's dimensions must be toleranced. A dimension that doesn't have a tolerance cannot be attained. Well, reference dimensions don't have tolerances, and how can that be? Well, it's simple. Reference dimensions are not used in the manufacturing of parts. Reference dimensions exist for two reasons. The first is a dimension on an assembly drawing. And as I've explained earlier, since assembly drawings show assemblies, well, the tolerance of each part cannot be calculated, so an overall dimension on an assembly drawing cannot be used to manufacture the part. The second reason that justifies using reference dimensions is the never repeat rule. And that rule is fundamental for drafting. And it states that a dimension can only be seen or calculated in one way on a print. If there's two ways of finding the same dimension, well, that is wrong. And one of those two dimensions should appear as a reference dimension. Now, here we're looking at the assembly drawing of a V-block project. And since there are no dimensions on this assembly drawing, well, there's no tolerances stated anywhere on the print, neither specifically on the drawing itself or in the header. If the assembly drawing does have a dimension affixed to it, as is the case with this hammer project assembly drawing, well, that dimension has got to be a reference dimension and is not usable for manufacturing the part. In this case, the reference dimensions are indicated by brackets, and that is the more acceptable and modern way of indicating that a dimension is a reference dimension, using brackets. For an example of a reference dimension being used because of the never repeat law, let's take a look at the clamp of this detailed drawing of our V-block project. We can see here that the 990 thousandths of an inch dimension is marked as reference by using the REF suffix, which means reference. Now, this is an older way of indicating a reference dimension, but it's still widely used. Now, the 990 thousandths of an inch dimension is indicated as a reference dimension because it can be found in two ways. There's obviously the one that we're looking at, 990 thousandths of an inch, but I can also find that same dimension by dividing the 1 inch 600 thousandths of an inch dimension that we see here in two, and then adding that to the 190 thousandths of an inch dimension between the center of the hole and the end of the part. And that will give me the same 990 thousandths of an inch. And since I can find the dimension two ways and end up with the same fundamental dimension but with different tolerances, well, one of the two ways is going to have to be marked as a reference. And in this case, since the 1 inch 600 thou is crucial for the spacing of my holes, well, the 990 thousandths of an inch dimension is going to have to be indicated as being a reference only. Okay, well, that's enough about reference dimensions. We were supposed to be talking about tolerances. So let's take a look down at the bottom right side of this print to see what the header looks like and what it indicates to us as far as general tolerances go for this drawing. Here in this little box of the header, we have our information for our general tolerances, and we can see that unless otherwise specified, the dimensions on this print are imperial. That if we have one decimal point or one number after the decimal point, we have a tolerance of plus or minus 15 thousandths of an inch on that dimension. Two numbers after the decimal point is plus or minus 5 thousandths of an inch. Three numbers after the decimal, plus or minus 2 thousandths of an inch. If we have a fractional dimension, it has a tolerance of plus or minus 1/64. And if we have any angles on the print, well, their tolerances are plus or minus 15 minutes, or if you prefer, a quarter of a degree. That means that this 400 thou dimension, since it has two numbers after the decimal point, will be acceptable if it measures anywhere between 405 thousandths of an inch and 395 thousandths of an inch. As for this 1.7 or 1 inch 700 thou dimension, since it has three numbers after the decimal point, well, it'll be acceptable anywhere from 1 inch 702 thousandths and 1 inch 698 thousandths of an inch. As for this 17/64th fractional dimension on this hole, well, that indicates that I have a tolerance of plus or minus a 64th because it's a fractional dimension. And that means that this hole will be acceptable if it measures anywhere between and including 8 30-seconds right up to 9 30-seconds of an inch. If we back off a little bit and see our whole drawing, we'll find quite rapidly that there are no specific tolerances on this print. So if we want to see specific tolerances, well, we'll have to change drawings. But there is, however, a very bizarre note. The note says that the V must be centered on the block to plus or minus 1/1000th of an inch, and that seems to be some type of tolerancing. In reality, it's a very gauche way of trying to tolerance symmetry, and that really should be left up to geometric tolerancing. But since we haven't seen specific tolerances yet, we'll get back to the geometrics later. Now, here's a drawing that does incorporate some specific tolerances, and it's the detailed drawing of our screwjack project. Most of the dimensions on this drawing are bilateral toleranced general tolerances, and their tolerance is given in the header as we've just seen. Bilateral because they are plus or minus from the base dimension. However, there are a few specific tolerances, and two of those tolerances are expressed as unilateral tolerances. The first one we see here is a unilateral tolerance. It's really 0.5 minus 1 thou minus 5 thou. But it's expressed in its limit form, and that's why we have 0.499 or 499 thou and 495. That's just the limit way of expressing it, instead of saying 0.5 minus 1 minus 5. We also have this tolerance down here. Now we have 0.5 or 505 thousandths of an inch and 500 thousandths of an inch. It's unilateral from its base dimension of 0.5. We have 0.5 minus 0 plus 5. But again, here it's expressed in its limits form. Now, you'd think that'd be all, but you'd be sadly mistaken, because there is another specific tolerance on this drawing. Actually, there's several, but they're all the same. And that's this 2 in the 2B, or the 2 in the 2A, or the 2 in the 2A down here. That is the class of fit for the threads to cut. And that is another way of expressing a specific tolerance. So I think we're starting to get a hold of this tolerance thing as far as dimensions go. But if you recall, a few drawings back, we were looking at the detailed drawing of a V-block. And we said that there was a very bizarre note on that drawing. And that note said that the V had to be centered on the block within 1/1000th of an inch. The note is bizarre because we're trying to dimension and tolerance an ideal. Now, when you apply a tolerance to a dimension, well, that's pretty straightforward. But symmetry isn't a dimension, it's a state of mind, it's an ideal, and you can't put a tolerance on that, not a dimensional tolerance anyways. Now, what that note is really trying to say is that the block has a width, and the width on the block has a tolerance, and regardless of the size of your block within that tolerance, we want the V to be centered within 1/1000th of an inch. That's very different from what we would normally see, and that is exactly why we would want to use geometric tolerancing. Things like flatness, perpendicularity, parallelism, position, roundness are all geometric descriptions and fall in the realm of geometric tolerancing. So let's take a look at the symbols for geometric tolerancing, and then we'll take a quick look at how they are applied on a drawing.
Here's a list of the most common symbols used in geometric tolerancing, and the list starts with straightness. When two surfaces intersect, they form a line. How straight does that line need to be? That is what is defined as straightness. The next one is flatness. Really have to be careful here to not confuse flatness with level. A surface can be level only when it's flat, but it can be flat without being level. In other words, a tabletop can be flat when the table is standing normally on the floor, but the tabletop isn't any less flat if you lift it and lean it up onto a wall. We can define flatness as being a surface that doesn't deviate from a normal plane. The next one is roundness, and roundness refers to the circularity of a part at a given position. If you want to know how circular a part is along its whole length, let's say like a pin, well then you're talking about cylindricity. If a line isn't round or part round, in other words, if it isn't an arc, but it isn't straight either, well then we call it profiled. The same applies to a surface. So we can have profile of a line or profile of a surface. These are often called irregular curves, and in the case of surfaces, they can be either two-dimensional or three-dimensional. The next three are what's called related geometric tolerances, and that's because they have to relate to another surface to be able to exist, and that's angularity, perpendicularity, and parallelism. Now, something that is angular has to be angular in relation to something else. The same goes with perpendicularity and parallelism. A thing or surface cannot be parallel to nothing. It's got to be parallel to something else. And that generally implies that that something else already has a geometric tolerance applied to it. Let's say flatness or straightness. If you want something to be angularly correct to something else, well, that something else had better be flat before you figure if the second surface is at its proper angle to it. Position could be position from, as an example, another hole, but it's often position from a reference point in X and Y. Concentricity, however, is in relation to an axis, and that could be a rotating axis or just the center of a cylindrical part. The last one on our short list here is symmetry, and a part can be symmetrical about a point, but as a general rule, symmetry is indicated as being equal side to side from a line, which is most often a center line. And if we had used this symmetry to tolerance the centering of the V on that V block drawing that we were looking at the start of this, well, we could have dispensed with that awkward note that was trying to tell us as clearly as possible that the V had to be centered on the block regardless of the block's width. Since symmetry is about the center line in this case, well, the block's width would have no effect on how to position the V on the block if geometric symmetry tolerancing was applied.
And that is the beauty of geometric tolerancing. But it's not just to save us from having to write bizarre or not very poetic notes on our drawing. It saves us money and time as well, because geometric tolerances permit us to make a part accurately without killing it with dimensional tolerances. What do I mean by that? Well, the block that we were just looking at, the 1, 2, 3 block, the V block. Well, that block didn't have to be very dimensionally accurate. Its width was 2 inches plus or minus 2/1000ths of an inch. Not terribly accurate. But we did want that V right in the middle. So the block had to be square. Its outside surfaces had to be parallel as well. And we wanted that V within a thou in the center. But its dimensions weren't that crucial. Now, it's one thing to make a block square, parallel, and to center a V, and it's another to make it dimensionally very accurate. And what costs the most money in those two is really the dimensional accuracy. Another example of that, maybe a little simpler example because we can relate it to a machining operation, would be a very simple parallel bar here, a 1-inch parallel bar. Now what's important with this bar? Well, what's important is that the top be parallel to the bottom and that one of the two be very flat, because if one of the two is flat and the other is parallel to it, well, they'll both be flat. But its actual dimension isn't that important. How would I obtain this? Well, quite simply, because it's a simple example, it's something we can relate to. Well, if I were to mount this on an angle plate and grind one surface flat, and then use that surface on the magnetic chuck of a surface grinder, support it with a very square block, and grind the second surface, well, my two surfaces would be quite parallel. Anyways, parallel within 1/1000ths of an inch without too much difficulty. And that would be the end of it, because my dimension here, let's say my height had a very loose tolerance, I wouldn't have to go out of my way to grind, measure, and work my way close to something very accurate. No, what I wanted here is it to be parallel. So if I could say I want this bar to be 1 inch plus or minus, I don't know, 5/1000ths of an inch, and that I wanted, however, it to be parallel within 1/1000ths of an inch and quite flat, well, then I would use geometric tolerancing for flatness and parallelism and dimensional tolerance for the height of the part. Let's head over to the whiteboard and take a look at what that could look like. So here we have a little sketch of our parallel bar in blue here, and everything's out of whack. I mean, my tolerance and my dimensions are way too big for the sketch, but I want things to be visible. So here in blue is my parallel bar, 1 inch plus or minus 5 in black. That's my dimension and my dimensional tolerance, 5/1000ths of an inch plus or minus to 1 inch. So 1 inch 5/1000ths, right down to 995/1000ths of an inch. Anything in there is good as far as height goes. That's not terribly accurate, but I do want the part to be parallel, and for that I need two things. I need flatness and I need parallelism. So here I have flatness to within 1/1000ths of an inch, and the part is flat to itself. A flatness does not refer to another part of the piece that we're looking at. It's just flat, okay? So flat within 1/1000th of an inch for this surface here indicated by the arrow, and parallel to 2/1000ths of an inch for this surface, but parallel is related. Related to what? To another surface. And the A here relates to the datum A, or if you prefer, reference A. So this lower surface, the one that is touched by the red triangle here, that's usually black. I'm just putting colors here to make things a little more visible. But this surface here, the one that touches the red triangle and that's marked as A, is my datum A, or my A reference surface. And that means that when I read up here the callout, this means that this surface here must be parallel to within 2/1000ths of an inch to that datum surface A. And with that, I have an accurate part that is easier to produce because it's not within a few 10,000ths of an inch. Now, what would I have done to the dimensions of this part if I hadn't had geometric tolerances? Well, I would have toleranced it to death. In other words, I would have put 1 inch height, but with a plus or minus of a few 10,000ths, with the hope that that would end up giving me 2 parallel surfaces. And because it would have been incredibly accurate, well, it would have been very expensive to produce. That's the beauty of geometric tolerances. So let's take a few minutes and go look at one drawing that I do have that has some geometric tolerances on it, just so that we can see what it would look like on a real drawing.
Here we have a combination assembly and detail drawing of a small precision machinist vise. Now, this is a precision machinist vise because the vise jaw, the movable jaw, when tightened down onto the part, is also tightened down onto the base of the vise, thus ensuring that this movable jaw, which is quite different from the others, cannot lift the part when it's tightened in. So this is a precision machinist vise. It's a lot less versatile or rapid to use than a regular machine vise, but it is a lot more accurate. So this isn't a tool mechanics course, it's a blueprint reading course, and what really interests us here is this the geometric tolerance. And if we read it as we see it, we can say that this surface, the surface touched by the triangle, should be perpendicular to within a tolerance zone of 0.03 of a millimeter to reference F. And this surface also has to be flat within 0.03 of a millimeter. Now, flatness isn't referred to F because flatness isn't a related geometric tolerance. In other words, if something is perpendicular, well, it has to be perpendicular to something else. But if something is flat, it cannot be flat to something else. Flatness is an ideal. And where is my reference surface F? Well, it's right over here. And it's indicated, again, by the triangle and the block with the F inside. This means reference or datum surface. In this case, datum surface F. Here we have drawing 2 of 2 drawings on, again, our machinist vise project. And in this case, it's just a detailed drawing because although we do have several parts on it, there is no assembly on this second drawing. And again, here we can see that we're using geometric tolerances. Let's start by looking at this one. If we read it, we can see that the surface indicated by the triangle must be perpendicular within 0.03 of a millimeter to datum or reference surfaces A and B. This surface must also be flat within 0.03 of a millimeter, and this surface is also reference or datum surface C. If we look over here now, we can see that the bottom surface of this front view has to be flat within 0.05 of a millimeter. and that this bottom surface is also datum or reference surface A. And if we look here, we can see that this surface needs to be parallel within 5/100ths of a millimeter to that datum surface A. And finally, for this view, this vertical surface needs to be parallel to within 3/100th of a millimeter to datum or reference surface C. If we take a look over here at the right side view, we can see that we have a similar series of geometric tolerances indicated. If we read them, we can see that this one here indicates that this surface needs to be parallel to within 3/100ths of an inch to datum or reference surface B. And this one here indicates that this surface needs to be perpendicular to within 3/100ths of a millimeter to reference surface A, and that it has to be flat to within 3/100ths of a millimeter, and that it is also datum or reference surface B. So I think we're getting the hang of this, but before we leave this drawing, I'd like to focus your attention on the 38F7 that we see here and the 6H7 that we see here, and just remind you that those are metric classifications for fits, and that is also a way of tolerancing a dimension.
Well, there you go. Geometric tolerances. But that's really just an introduction. The main objective of looking at those geometric tolerances now, well, is just to let us know that they exist and to keep an eye out for them. But it's really something that's more for an advanced student, and we're doing introduction level a course here. But hey, you know it exists and you have a general idea of how it works, and that will give you a good start if ever you decide to investigate a little further. And if you want to investigate a little further, well, I recommend that you find a good book for that and read up on tolerances and geometric tolerances, and why not at the same time blueprint reading altogether. And for me, one book that I really like, well, is this Interpreting Engineering Drawings that was written by Cecil H. Jensen. And these days, because Mr. Jensen passed away, well, it's been taken up by J.D. Helzel. So, excellent book. I don't recommend this book, but this is one that I like. I don't recommend because I don't do product placement and I'm not doing this for money. So, but you know, look it up and or another similar book. But I must admit that I like this one quite a bit. And that can help you. Now, I've managed to lie to you once again, because at the start of these videos I say, well, this is what we're going to look at today, and then things just sort of get out of hand because I don't plan these videos very well. I sort of know where I want to go, but I'm not sure how I'm going to get there when I start, and that's part of the fun of doing this. And I don't want to change that. I don't want it to become too well prepared and serious. But that does mean that we're definitely going to have a part 4, because I didn't get to where I wanted to get to with this video, and it's been long enough for now for this part 3. So there will be a part 4, and in that part 4 I hope that we'll get to actually learning how to read a blueprint. That's the main objective of this lesson 4. And maybe, who knows, maybe even a part 5. But anyways, thanks for watching, and look out, keep an eye out for part 4 and eventually part 5 maybe. And in the meantime, we'll have fun and be careful, and well, as always, happy machining. There you go.